They're on the CPU, so they're quick access. But okay, but the point is, basically, they can be used for specific capabilities. So let's say you wanted to find out, and this is how something like Gmer or Toluca would do it. They would go and they'd say, okay, I want to see if the syscenter EIP that the syscenter is going to be pointing at, I want to see if that's pointing at the KI fast system call or whatever it was called. So it should always be pointing at that one particular thing in kernel space. And so what they would do is they'd say, okay, move 176 to ECX, and then they do read MSR. And that'll read the 64-bit register into EDX, concatenated with EAX. So the lower 32 bits are going to be in EAX. So I just say EAX now contains the value here because this particular 64-bit one, the upper bits don't matter because this is being used for 32-bit value. So that would be how you would read out the MSR and say, what's in it currently, and then you'd compare it. You'd say, does this 32-bit offset look like the address of KI fast call entry or whatever it was? Simultaneously, let's say you wanted, if you were a rootkit and you wanted to hook this thing and you wanted to make it so that when someone calls syscenter, it doesn't point at the default thing anymore. It points at your code instead. Then what you do is you'd set EAX to the place you want it to be. This would be the target of, this would be EIP, which is going to be used when the syscenter is called. So you'd set that to the EIP that you want. You'd set ECX again to be the MSR that you want to deal with. And then you just call write MSR. And then at that point, it would take that and it would write it into this model-specific register. And there was actually an example of this in the Rootkits class there, or in the homework. So going into this, if you scroll towards the top of your Gmer results, for instance, and past the SSDP, right here. So in your Gmer results, there's a field where it says type is syscenter. And all it did was it went in, it called the read MSR function on MSR number 176, and it said, okay, I got the value out. The literal value was F8 dB blah, blah, blah. That is not pointing at the correct default value of KI fast syscall. Whatever. The name again. Stop saying whatever. KI fast call entry. Right? So syscenter on a normal Windows system should always point into KI fast call entry in NTOS kernel.exe or NT kernel PA. Right? And so just by reading out that MSR value, you can see the attacker has changed this so that in the VM, it now points to F8, D8, B, etc., etc. And so that's how you see it in Gmer. And in Luca, it has a specific thing here as well, where it's saying, interesting, it's saying suspicious is no, even though it's clearly calling out that this is not pointing at the default entry. So that's interesting. But it didn't put it in as red, but like I said, typically Gmer will only put things in red if it is something associated with a known rootkit. So for all the other changes, they just say, here's the change, that's your problem to figure out. But they only ever put things in red if it's due to a rootkit that they know about. Actually, let me see if I can find that quick. There's actually a little file for Gmer where it'll say, here's the specific things I'm looking for that I'll consider a rootkit. And it's interesting because then you can see what some rootkits do just based on this list. So let's say kit I think this is it. No, that's not it. All right, I'll remind myself to go find that at the next break.
Are the right?
Yep, good question. right? The read MSR, write MSR are actually restricted to ring 0 only. So these are examples where only ring 0 code is allowed to issue these commands, because otherwise user space code could just point it wherever and crash the system at a whim. So that is correct. And similarly, it would only make sense for an attacker to actually use them if they were already in kernel space in order to target it at their code. All right, small correction on your slides. If you're planning on using them in the future, I put literal read MSR and write MSR, but it's actually RD MSR and WR MSR. All right, so that's an example of how you can see the changes which are being made to an MSR. And actually, I just wanted to show quick in the Intel manual, you can go see what all the MSRs are and what they're used for. At the end of section 2B, or 3B actually, in the appendices of Intel Manuals Volume 3B, Appendix B has all the MSRs. So you can literally just go in here, you'll find all the mnemonics and stuff like that. You find what they're used for. And so if we try to go find the, yeah, so this one, for instance, I was just looking through this the other day to see if there's anything that looked kind of interesting that I hadn't seen before. So remember I was talking a little bit before about the BIOS can have microcode updates for the CPU in it, which get applied when the BIOS is loaded. There's actually an MSR that can say whether or not an update to the microcode should occur. And let me see, would this be set by the BIOS or not? Yeah, I think this is the kind of thing where it would be set by the BIOS. So the BIOS would execute. It would check the version of the microcode currently in the CPU. It would check the version that it's holding to see, do I need to update the CPU? And then if it does, it's probably going to write into this MSR to say, trigger the update, and then it's, going to do a reboot or whatever it has to do in order to get that microcode applied to the CPU. So there's various interesting things in here: SMM monitor configuration, stuff like that. But all of these, so okay, there we go, sorry. So last thing, so actually, I'm not going to go into it, but in the sysenter instruction, it actually uses a bunch of simplifying assumptions, which I think are largely behind the performance gains versus using an interrupt. So we said sysenter is how you're supposed to go from user space to kernel space now, but it can only be used in specific condition, and that condition is this other register, sysenter CS, is pointing at so CS is like, a code segment register. It should have a segment selector in it that selects a segment that starts at 0 and goes to 4 gigabytes. Right? We said by default everything pretty much does that anyways nowadays, but this is now kind of really codifying it that if you want to use sysenter, you must use segments from 0 to maximum, and you must set CS to point at one of them, and then actually the next entry in the GDT has to be, so whereas this is code segment, the next entry is going to be assumed to be the data segment, the SS register, which will be used with this ESP. So we said, you're always implicitly using a logical address, and here you're basically just setting it up to use, CS : EIP. So there's your CS, there's your EIP, and then it actually just assumes that whatever the thing in the GDT is after the CS you're pointing at, that's the thing that'll be used for SS. So that's SS, and there's your ESP. So between the two of those, you have a code logical address and you've got a data logical address. And those are what are used when you call sysenter to transition into kernel space. So you can go look up the sysenter instruction in the manual if you want to see more about that. But it's just interesting that they're now kind of really codifying that you must use those simple, giant, cover all of memory segments. Because no one was using anything more complicated than that anyway, so no one was losing out. All right. So anyways, wander around in the MSR thing later. Is there a question on the phone? No. All right. So you can wander around through the MSR thing later, seeing what sort of miscellaneous stuff they have there. All right. And here's some more references where if you'd like to go read those, they'll talk more about the system call transitions that we were just talking about. All right, so that was just talking about, the potential for hooking syscenter. We said it's really just syscenter has these MSRs that are controlling it, specifically that EIP one. And one of our proof of concept rootkits here, all it did was it went in and wrote that to point at the attacker's code. And it was literally just a pass-through. It just immediately went to the original. But, well, before I move on, right? But when the attacker controls this syscenter EIP thing, he basically can man in the middle all of these calls to the system service descriptor table, right? He is sitting at this level, right? So when you're transitioning, instead of going here, you're going to the attacker code. And now before you call to any of those entries in those tables, the attacker can manipulate where you're actually going without having to change those tables. So he can look at your EAX, and before he even bothers to parse any of those tables, he can say, I know for this particular EAX, it corresponds to, write file, and then he's going to, control your EIP and make you go to his write file instead. All right, so that was about hooking syscenter a little bit. So the other new hooking technique, which we hadn't had prior exposure to, was hooking the SSDT. And this probably needs to get redone a little bit. This is a WinDebug command that you can use to see each of those pointers to the SSDT at the thread level. So this will go to every single thread. It'll say, where is this pointing? It should be pointing at this one or that one, the regular SSDT or the shadow SSDT. And if you were to issue that command and if you were to see 3 possible values, then something's up with that third one. You need to figure out which one's normal SSDT, which one's shadow SSDT. If there's any third ones in there, that means someone's pointing to per thread hooks.
Isn't that a bad idea? Why didn't they just have a bit saying one or the other? Since then it gives you a place to address.
Well, yeah, why didn't they just have it be one or the other? I would think it's for, well, I would guess it has to do with, simplicity of the code, which parses the AX and parses the thread information. If you say it has to be one or the other, the question becomes, how does that code know where the one or the other is? So it's still going to have some data structure somewhere that points at one or the other, right? And yes, the bit could say point that way or that way, but, in the simple case, there'd be like 2 function pointers, right? But then the attacker could just, or not even function pointers, just data pointers. The attacker could just come in and replace a data pointer, and so the 0 or 1 would no longer be telling you is it good or bad, because one of them could just be bad. It could just be a copy that has malicious stuff pointed to. So I don't think that would really buy you anything. Kind of, most of these OS design level decisions are such that you assume there's no attacker in the kernel potentially manipulating stuff, right? When you start working from those assumptions, things become harder. All right, so again, this is, nope, this is not the black energy. So one thing I wanted to talk about is very few of the tools that you could have run would have found this type of manipulation, but there is a function called KE add system service table, and this function, I'm going to this in here, indicate that's a function. There's a function called KE add system service descriptor table, and He4Hook, which is one of the rootkits which I've installed here, uses this function in order to add an extra, quote SSDT, and it uses that in order to communicate between user space and kernel space. And so this is another case where there should only be certain things in those. Well, I'll just get through it and go right here. All right. So specifically, it's in that shadow SSDT thing we were talking about. There's 4 structures here, right? In the normal case, let me use something. All right. In the normal case, on a system that has no IIS, Microsoft, whatever it is, Internet Information System Services, whatever it is, IIS their web server. If you have no IIS web server installed, this is what this KE service descriptor table shadow would look like. You would have the native API, you would have the Win32 one, and then there would be nothing there, nothing there. And when you call KE add system service table, that function basically fills in entries into these things. And actually, this Win32K entry was added by the OS calling this function, and then it adds in that Win32K entry. So this is meant to be sort of an extensible thing. Similarly, when you have IIS installed, it adds in this IIS spud.sys thing, which is going to point out to its own base, and it's going to have some array of function pointers which can be called from the user space side of IIS to the kernel space side of things. Now, what an attacker can do, and this isn't necessarily related to hiding. This is potentially more like a backdoor kind of thing or back channel communication. If the attacker calls this function, as he for hook does, what happens is they get put into this array of 4 possible entries. And so now, let's see, oh, I don't have it. All right, well, I need a new slide here, but I'm going to do this on the board. All right. Bill, can we go over to the board? So, whereas the normal thing is going to have 4 entries, and so the base of this thing is going to point out to some table like that, and the base of that thing is going to point out to some table like that. Right? And there's many entries in each of those. That's a normal system with your normal SSDT and your shadow SSDT in that case. Now, when he for hook comes in and it calls this K add system service table, it adds a pointer to this little table like this, which has, I believe, like 5 entries in it. And so for these 5 entries, what the user space side of the code does is if the user space side of the code says, move EAX, it would be 2001 or something like that. But let's go with 2000 just to be simple to start with. Right, so, and then it does sysenter. The user space side of the code does this. It does move some hard-coded constant into EAX, call sysenter. That, works its way through the normal KI fast call entry, which parses the EAX, and it parses it, and it says that's index 2. Yeah, 2. So this is index 0, this is index 1, this is index 2. Then it goes ahead and it parses this correctly, and it sees, okay, take this base right here and add, take that base, that points at a table, and then take these 12 bits. Those 12 bits are an offset into that table, so let's say the offset is 0, and then call that function right there. And that function then points into, these functions all point into for hook. And these are sort of control functions that, so the user space side can control the kernel side to say, okay, I want you to now add a new file to hide, for instance. So user space side has this little API where it calls through these SSDTs in order to send commands to the kernel space side. Now that's a particularly uncommon way of doing things, but I thought it still warranted description because that could be caught by, looking at this level. We expect this is going to always point at a particular location for that table. This is going to point for that table. These should be unused unless there's IIS installed, in which case there should be something there, but there should almost certainly never be anything there. So if you had IIS plus he for hook, there shouldn't be anything there. So you could find that sort of back channel communication mechanism, but then they would just go to using IO control, which is the more proper way to do things, and that would be harder to find. So that was just worth mentioning because some tools will tell you this. I think only the one tool we run at the end of tomorrow will will even acknowledge that this sort of thing is going on. But that, again, just speaks to the importance of having the tools, knowing what the tools can and cannot find, right? That's the point of that Excel file, saying this can find this. Knowing what they can and can't find, and whether it's relevant, whether you think it's relevant for, finding the malware, finding rootkits. All right. So, anyways, the point here was just, again, to call back to the man-in-the-middle notion. For this entire process of SSDT hooking, well, yeah, so this is what I didn't really talk about, but we've kind of already covered it a couple of times anyways. The point is, we know that an attacker can go into this table, like those tables on the board there. You go into it's just a big table of function pointers. If the attacker points it at their own function, then obviously they will have the opportunity to man in the middle. And so the point is, there's many, many places along the path of, from user space to kernel space where an attacker can gain control. Along that boundary, that's where you could, the transition between user space and kernel space, that's either the interrupt-based transition or sysenter transition. But in either case, there's an opportunity for the attacker. They're kind of on the kernel space side of things, but they're still able to immediately control at that transition. When that transition goes to KI, fast call entry or anything like that, they can grab control again. When they go to whatever functions in the SSDT, they can grab control again. When they go to the function, they can grab control again with an inline hook. So many opportunities here, and you have to know of these opportunities, and then you have to know which tools will detect what along this path. And then there can also be issues of false positives in your tools. So I previously talked about, the McAfee false positives where they put inline jump instructions in your kernel. Then you can have this case where Symantec, for instance, will have false positives that are actually very difficult in order to attribute to Symantec. So this would be like Symantec Enterprise Protection. For all of these SSDT entries, which unfortunately doesn't tell me their index, but in Gmer, were you to run SEP on one of these systems that has, if you were to run Gmer on one of these systems that has SEP installed, you'd see something like this. And the problem is, Gmer is trying to look up that 81EB36A0. It's trying to look that up, and it's saying, this doesn't correspond to any kernel module that I know about. And that turns out to be because this is actually dynamically allocated memory. So Symantec creates some space on the heap, copies some code to there, some little stub code, which is going to have the hook code. And then when an SSD entry is called, it calls to this Symantec stub code, which calls to Symantec, and then eventually it calls the original. The problem is when you can't attribute it like that, how do you know that this is Symantec versus some bad guy who just did the exact same thing? Create some space on the heap, copy some code there, and hook. And so this is, again, one of the things in the TiddlyWiki where I go in and show how you would actually have to look at this in order to say, okay, this is or isn't Symantec doing these sort of hooks. So specifically in the case of our VM, all right, so I said there's sysenter, which is causing hooks, and that's, that was a malicious sysenter.sys that I put on the system. Then you can see there's a ton of SSDT things that are listed here, right? Then the question becomes, what's malicious, what's not, who's doing what, all these sort of things. So one thing here is trustier rapport, which is something which is trying to do, well, I think what they're trying to do is looking for people, looking for malware that's, stealing your banking credentials, like keystroke logging, while you're connecting to your bank's website or something like that. So they're kind of trying to stop keystroke logging. But, in trying to stop the malware, they've put themselves in a ton of places on the system, but at least they're roughly attributable to them. Again, with all of these, quote, attributions, you always have to ask yourself, is this rapport PG or is this malware that's just named itself that, right? So you kind of don't know unless you have some trusted path to get binaries and all that. Actually, though, do want to go over to Toluca quick. I want to see if it can do checking of driver signatures. No, it can't. So I think at this point I want to pull down the virus block ADA tool because I know that that can do digital signature checking. So, well, let me see. Before I lose my train of thought. Yeah, that's fine. So we're gonna pull down virus block ADA in order to have this thing which I'm claiming is one of the best tools. So the path for that is, the last class I didn't realize that the beta version is not on their main site. So you need to grab from this directory. So inside of your VM, in Internet Explorer, put in ftp://beta/VBA32 ARKit underscore beta.zip. For that. Save it to your desktop. Unzip it. Now, at least in this case, I do know that it is going to go out, try to go out to the network, but I did look at its network traffic, and it is trying to consult with the VeriSign certificate revocation lists. So they say they're doing that specifically because of the Stuxnet case where it has a valid digital signature, but they're trying to go out and see, is this digital signature revoked because, they revoked the ones that were used for Stuxnet. So, what do you got? Not finishing it? I'm not going to because I want to switch between the different things to show how they look. If you put it in this mode, it's not going to let you switch out to apps. And I think the whole point of this mode is that it's going to set the system so that no new processes can launch, no new kernel drivers can launch. So it's kind of like holding the system in steady state. I'm just going to run it in the non-blocking mode.
So we should say yes or no?
Typically, you should say yes. Right now, you can say no if you want, so you can go back and forth. All right, so like Gmer, this has a mode where you can just, scan. So you can click all these check marks, hit start, and then it'll go check everything. I just want to show a couple of things independently, so I'm not going to do it that way. Also, I'm going to turn off the, I'm going to leave that on. I'm going to leave the checking digital signatures on. That's why I said I was coming here. But I'm just going to block it with Zona 1. So under Tools, this is where you can get to the specific different types of checks if you don't want to run the full scan. So I'm going to go to kernel mode hooks. So Tools, kernel mode hooks. And then this is going to scan for a bunch of stuff like SSDT changes, I think inline hooks, IAT hooks, EAT hooks. And then, of course, this time it's once again too big for my screen. Awesome. All right, so if it's asking to go out to the network, say no, deny it, and remember this setting. I'm going to go up, try to check VeriSign certificate revocation lists. What? Yeah, I think just move it over to the side and then click that. Yeah, so if it's too big for your VM as well, move it to the side and then click the little maximize window, this one right there. Yep. So this looks like it's saying, here's some IAT modifications, here's some EAT modifications. Notice that Gmer didn't say anything about EAT modifications before. That's export address table modifications. Is yours working? Yeah, so go to Tools. And then, oh, so you clicked on the full one. So hit cancel and see if that will stop it. You may have to quit it, open again, and just go to Tools. But yeah, if you do the full run, then it takes forever. So EAT modifications, Gmer didn't actually tell us about that, and let's see who's to blame here. Looks like that's VS data nt.sys, that's zone alarm again. So export address table modifications, we said the reason an attacker, or in this case, zone alarm, would want to do export address table modification is that you can, when you inject something into a module's memory space and you change all the IAT entries, that just changes whatever is there right now. But if something new comes in along later, so if a new DLL gets loaded or a new kernel module gets loaded, your code would have to go in and modify the IAT for this new stuff. But if instead you just modify the export address table so that the offset, the quote offset to this function is completely outside of the scope of that particular module and it points all the way offsetting to the attacker code, then the OS basically just does your job for you. The next time something loads, the base address plus the offset equals the attacker code, and the OS loader fills that into the IAT of the new thing. All right, so as you're seeing, it's running through processing stuff. Green is coming up for things which you can verify the digital signature for, and for things which you can't, that shows up. Well, things which you can't or things which are locked file, those show up in red or yellow or whatever. So the nice thing here, the big thing I want to say here is with VBA, basically everything that shows up in this view, you can roll back. So for all these IAT modifications, you right-click and you can click Restore. Don't click Restore. You'll probably blue screen your box. Because if you roll back everything all at once, then it's probably fine. But sometimes if you roll back one change but not the others, then it'll blue screen. So don't do that. But the point is, you could do it if you wanted to. So all these IAT, EAT, etc., these things can all be rolled back. So here's a code modification. This is like a .text section modification. That was the one by debug view, dbgv.sys. So you can roll that back. Debug view will never again show you any of these changes. And so, this is kind of relevant both for, reverting rootkit changes as well as messing with security software. So the point is, if you roll back the security software changes, most of them are not smart enough to put their changes back. And therefore, if you roll back these changes, all of a sudden zone alarm will stop filtering all of your network traffic, right? And so security tools definitely need to up their game because if an attacker comes in, they can just roll back all the changes. The security software is blind. And we've used that for proof of concept attacks in the past in order to show certain security vendors that they're not so hot. All right, so then still there's all these SSDT entries. And so looking for ones which are not in green, so this is the nice thing here is that you can focus on things that are not green, and you can actually, if you want, you can click Don't Display Trusted Items, and then all that green stuff will go away. And suddenly you're left with a much more manageable list of changes, right? So as long as the third-party software is at least going to the trouble of signing their code, that will help eliminate some of these things to the degree that you trust that signed code is automatically trustworthy, which you shouldn't necessarily, because again, Stuxnet had signed drivers. They stole a digital signature, right? And then they signed their code. But the point is, this is always where you want to start. For everything that's unsigned, start there, and then go ahead and check, add the signed stuff back in later. So, for instance, here's that IAT hook, right? Int E. If we wanted, we could just restore this, and then all of a sudden, ShadowWalker is no longer, hiding memory. Sysenter right here, saying IA32 sysenter EIP, could restore that, and no longer is that proof of concept code interposing on that. So this is some of the, so this should be one of the lessons learned coming out of this class is that you use the appropriate tools, and for that restoration portion of the homework, I said, how can you remove the changes? One way is you can try to identify where the changes come from, remove those files. Other way is you can use appropriate tools. Now the point is, if you just do this, if you just restore this, the next time you reboot, it's going to be back, right? So that's not necessarily going to be the best way to remove rootkit changes, right? You probably want to still identify which files are causing them and remove those files. But removing the hooks is a good first start, because then if they're hiding their files or they're blocking you from accessing their files, then if you remove their hooks, that stops them from blocking you. And then as long as you know which files to remove, then you can do so. So that's what I want to say here. I think the only... Yep, so this is literally the only, out of all those tons of SSDT changes, there's only one thing, which is the actual rootkit here. It's this control ctr12cap.sys. This thing is trying to impersonate that it's control2cap.sys, which is a sysinternals tool, which is also installed. So if you look through some other mechanisms, you'd see, okay, control2cap is installed. You go Google control2cap, you see, okay, it's a sysinternals tool to say, you know, your caps lock key can be used as your control key, using a mechanism that we'll talk about later. And then were you to maybe go skimming through, you wouldn't necessarily notice this is a 1 instead of a L, and you'd say, okay, well, that's just the control to cap change. That all makes sense, right? But in reality, this is something where it's actually just trying to do some of that hiding in plain sight, blending in. It names itself like an existing file that it knows is on the system. And this one in particular, this is for those of you who found the hidden directory cool beans, _cool_ beans. This is just a modified, there's like one of the proof of concept files off of rootkit.com. It hid any directory or files that started with _cool. I think it was originally _root, and then they changed it to _cool. So I just made a folder called _cool_ beans, and then that was hidden. And this is the actual module which implements that. And how it implements it is that it's hooking the SSDT for the function ntquery directory file. And as the name sort of implies, ntquery directory is the thing which is called to list the files in a directory. So if you hook the thing which lists the files in the directory, you can remove files from the directory listing. And that's all this does. It hides anything. You know, if you go in here right now, you create a new directory called _cool_ anything else, it'll just immediately disappear because this thing's going to be hiding it. This was just a proof of concept thing off of rootkit.com, where it was like a basic hide file.sys or something like that. I have to check the team there. Which I don't think I have the wiki open anymore, so I don't know. All right. So anyways, you got false positives potentially for the SSDT. Only thing I wanted to say was that virus block Ada can roll back a bunch of those changes for anything that was found there. All right, any question on SSDT hooking before we go on? So we saw sort of hooking sysenter. We saw changing the actual table entries there, where this data structure that has 4 possible entries. Typically, the first entry is pointing at the, quote, normal SSDT entries, and then the next entry is pointing at graphical GDI entries. And so you can change the actual things in that function pointer table, and then the attacker gains control. Any questions about SSDT hooking? Anyone on the phone? All right. That's all we're going to say about SSDT. So SSDT was a new thing we hadn't really seen in other classes, and this next thing is as well. So this is I/O request packets, or IRPs. So IRPs are an abstraction layer within Windows that's generically used for input-output. So this can refer to input-output to, hard drive, network, keyboard, stuff like that. It can be used for a lot of different things. So, well, I think the picture describes it best. I'm going to come back to that in a second. There's 2 sort of objects that really matter here. There's driver objects, which correspond basically one-to-one to when you load a kernel driver into memory, you get a driver object. That actually gets passed to the main function of the driver entry function. it gets the kernel gives it gives it this data structure, the driver object. There's also then device objects, and this is what relates to I/O request packets, or IRPs. And the device objects are basically used to create a linked list saying, which driver objects want to find out about I/O requests. So this is a useful look at it. And actually, I haven't put in references into your book yet, but I really should. There's a good picture of this as well in, actually, it's my book. So there's actually a good description of this, chapter 8. If you look at page 461, you'll see an alternate version of this picture, which is sort of useful. I want you to see that quick because I didn't make an equivalent picture. I probably should have a little animation thing here, but on page 461, figure 8.2, this sort of shows the way that an IRP or I/O request packet sort of travels along this chain. So it starts at the top at the I/O manager, and then you've got this IRP, which you can think of as basically like an abstract blob of data that's going to a device. So that blob of data can be a packet, it can be some sector that you want written to the hard drive. And so basically it starts at the top and it keeps going down to each of these driver objects, and then they can say, the specific device can say whether it wants to hear about it or not. That was page 461. Those of you have their book late. 461, the picture at the top, figure 8.2. So the I/O request packet is sort of traveling along this chain from top to bottom, and each thing in this chain has an opportunity to say, I want to handle this I/O request, or I'm just going to pass this along. And so if everything says, I'm not going to handle this, it eventually gets to the bottom of the chain, it has to handle it. So in this particular case, I've showed what the I/O request chain looks like for the control to cap, which I said is a sysinternals tool, which I installed in the VM. And so control to cap actually attached to an existing chain. So before you install control to cap, there's this existing chain, these bottom 3 entries, right? And so control to cap basically attached to, it said, I want to see data that's being targeted for keyboard class 0, which is a device that pertains to the keyboard. And it's basically a device where keystroke information is going to be going. And so specifically what control to cap, I said control to cap is just used for switching the control key and the caps key. So you know that on some different systems, their keyboards have a control where the caps lock key is. I can't remember if it was Sun or who it was, but there's some keyboards out there that have it that way, and people like it that way, Unix type people. And so this control to cap is basically putting it itself into this chain so that it can find out when you're pressing the control or the caps lock key. And when it sees that coming down on this chain, when it sees that I/O request packet coming down or the data coming back up, it can say, I want to swap around what's actually happening on this system. So, yeah, so this is all I wanted to say here was that notionally you've got driver objects. Each of them can have a name, but they can also not have a name. So this is what you'd see if you actually look at it. It ends up not having a name for a bunch of these. And so, one second. Yeah, so what I'd want to say here is there's 2 possibilities for rootkit type behavior at dealing with these I/O request packets. The first one, can we go to the board? Sorry, the screen, Bill. The first opportunity for rootkit type things here, and we're thinking of man-in-the-middle level activity, is essentially exactly what control to cap is doing. We said up there at the top, like that picture, there's the I/O manager, which is passing these I/O request packets up and down this chain. So one thing you can do here is you can come in and you can interpose on this chain. You can say, I want to be at this level, or I want to be at that level. And so, maybe you're getting data that's being targeted to keyboard class 0. That could go right there. Or maybe you want data, that's being targeted to this actual raw device, something like that. So this is called attaching a filter driver. in that you want to filter data coming down or coming up, depending. And so you place your driver such that, I have those names backwards. You place your, yes, I have those names backwards. Oh, but you don't have the slide anyways. You place your driver, so you're loading up some new driver, and you know there's this chain of IO request packets somewhere that are going, up and down a stack, targeting some device, keyboard class 0 or some other lower device. And you know there's data in that chain that you want to intercept. It could be file data. So if the thing is eventually targeting like a hard drive, then you maybe want to intercept that file data and change the data, or just read the data. It could be keyboard data. In this case, this would be a chain where there's keystrokes moving up. You can conceptually think of them as keystrokes moving up and down the chain. You're pressing. It could be things like packets. You can similarly have a chain of IO request packets going for packet data and other things. So the first level of rootkit type inner position or man in the middling here is just loading up a driver and saying, for this particular thing, I want to be an upper driver. I want to, be above it in the chain, or I want to be a lower driver. And so that's what control to cap is doing right now. In the book, when it's done talking about this IO request packet, it goes on to give an example of keystroke logger, which looks basically exactly the same as this chain. Yep. So this is control to cap, but in the book, you'll actually see that there's a keystroke logger which places itself exactly where control to cap is, and it is basically filtering when this data comes down. And here's where I unfortunately have to get more detailed than I want to, and this may be confusing, and ask questions if this isn't clear. The IO control manager in this particular case of keystrokes, the IO control manager is preemptively sending down requests to say, hey, dear hardware, do you have any keystrokes yet? And so it's sending down an IRP, and it's going down, and then when the hardware says, yeah, I've got a keystroke, then there's these completion routines which occur where this says, here's the function I want to call when an IO request has been successfully when there's actually data that's coming back from the hardware down at the bottom level. So this says, I want to be called at this function when we find out that there's new data coming back. So this guy gets a callback, and maybe this one doesn't register a callback. Maybe this one does, and maybe this one does. So at each level here, driver has an option where it may register a callback that says, when this IO request goes down and when the hardware fields that request, I would like to hear about it, and here's my IO completion routine. And the IO manager is responsible for organizing all of that. And so in this particular case, the way it works is it's sending down these preemptive requests saying, dear hardware, do you have any keystrokes yet? And when it does get a keystroke, then it says, okay, this is handled now. It's got the data in this IO request packet. And then for each thing that registers a callback, the IO manager says, hey, you wanted to find out when an IO request has been processed? All right, here's the blob of IO request data, and I'm going to call your callback routine. Hey, here's the blob of data. I'm calling your callback routine. And it's because this thing up here is, in the chain that it gets to say, I want to find out when a keystroke is coming back, when it's been fielded, and that's how it actually sees the keystroke, when its completion routine is called. When it went down, and when it's going down, it registers the completion routine and says, I want to hear when this is done. And when it's done, then the IO manager comes back and says, hey, it's done. Here's the blob of data that I got. Do something with it if you know what to do with it, and all that sort of thing. All right, is that clear? Not sure on if that makes sense. Anyone have any question on that? Yep.
Position that you register to handle that. Can only one driver say I'm going to handle it right after a KBD class, or could you have two bootloaders trying to do it all the way through?
Fundamentally, only one thing can really be at one level, right? So it's sort of like there can be race conditions there, right? So you could have two keystroke loggers, right? I could have control to cap and my keystroke logger. And it's really a question of who registered first, that dictates who gets what position. There could be no functional difference in terms of what data they see, but in some cases there could be a difference. So can we go over to the board? So I probably should make another slide for this as well. But I'd done this description mostly on the board last time. So let's say you have something like a full disk encryption stuff. Well, let's start with your question first, right? So I'm just going to draw this. Let's say this is it keyboard class 0? Right, and so this is the thing which points at control to cap. And now the question is, who registered first? So keystroke loggers, we know at this point keystroke loggers can register above this keyboard class and see the data. Maybe they can register below, maybe they can't. But the question is, if you have two things which know that they can register above keyboard class 0, and they both do, what happens? Are they in parallel? Does one get it before the other? And the answer is that one does get it before the other, and then therefore it just becomes a question of who registered first. So if this control to cap registers first, if let's say there's, their drivers load alphabetically or something like that, so control to cap loads before, key sniff, or I think in the book it's like key logger. Something like that. So if control to cap loads first, this device this driver registers a device object, and it gets put into this chain. Now this driver comes along and registers another device object, and that also gets put in the chain. Now the thing, actually, because this guy came in second, and because he said, I know I want it exactly above keyboard class 0, then when the second guy comes in, his is actually going to be, put in at that level, right? So there's just sort of who registers first and what level they ask for ultimately dictates who gets what level. Now, the thing I wanted to say about, why, what level you're at, whether you're an upper driver or a lower driver, why it matters in some cases, is I'd give the example of, full disk encryption. Let's say there's full disk encryption thing, which is encrypting your data. And again, this is the point of having these sort of abstraction layers, is let's say this is device FDE, and let's say this is FDE.sys. Right, so these are the devices, these are the drivers. All right, so FDE.sys attached to, let's say, NTFS, something like that. So let's say there's an NTFS.sys, which there is, NTFS.sys. That's a kernel driver, and it created a device called just NTFS. And this is a device where you can send IO request packets to it if you want to write files to NTFS file system. So the FD, so originally there was nothing. There was just, some IO manager and NTFS. Then FDE comes along and registers this. Well, sorry. Let's say before FDE comes along, there's my rootkit, sys, whatever. Well, let's call it success, which is in reality MRX net sys, something like that. That registers, blah, maybe it's empty, maybe it's not, right? So let's say you've got something which is trying to intercept IO request packets that are going down and targeting at the file system because, for instance, it's trying to hide files on disk. In this case, let's say it's hiding those exploit files on the USB drives, right? This wants to see all IO request packets coming down saying, you know, are you trying to list a directory? If so, then when it comes back up and we've got that data, remember when these completion routines get called and they come back up, each completion routine gets this IO request packet, and so each of them could potentially manipulate the data as it comes up, goes down, etc. And so the point is, this guy's up here hiding files, right? But now let's say you've got a Stuxneted system and someone installs full disk encryption on it, right? And full disk encryption says, oh, I need to live right above NTFS, right? They install themselves, and they're still in the chain, and, well, in this case, I guess it's not actually going to make a difference, but I should have done it in the other order. Oh, well. Let's say the whole point of the FDE is that it also wants to see when data is going down, it's then doing the encryption so that when the data is ultimately written out, it's encrypted data. And then transparently, when the data is coming back up, it decrypts it so that everything looks normal up here. Now, in this case, it would make no difference. But what I was thinking of was more like if Stuxnet was at this level, then obviously, if the data comes down and the FDE is like, you know, encrypting the data, then all of a sudden this thing, which was expecting to see, you know, I'm really mixing things up here, but this thing which is expecting to see, you know, just regular file data coming down, it would all of a sudden see garbage. And so that's why the order here definitely matters, and the order of attachment matters because, well, because of examples like this where you've got something where data is being changed, or let's say you had, I could do another example like this where it'd be something like firewall. You know, zone alarm can be, and I think is, intercepting IO request packets being sent for network data. And so if zone alarm is at this level in the stack, but I come in here and I add my rootkit one level below it, then all of a sudden my rootkit is no longer subject to the firewall rules and stuff like that. So understanding that there's this sort of system going on is definitely important to know. You know, one, you want to know who should be in these sort of chains. And two, if you're a rootkit author, you need to know that these things can be messing with you if you're not put at the right level, and if something new gets added in, for instance, your stuff could just break. Right? But for our purposes, for detection, knowing who should be in these chains is important, because then you know who should or shouldn't be filtering this data, such as something like Stuxnet. All right. I think it's time for another break, and then I'll talk about the second way that you can man in the middle of this sort of data. It pertains to those little array of things right here, which turns out to be an array of function pointers. All right, 5 minutes.